Okay, let's take a look at part 2 of chapter 1 review. I've skipped a couple of problems in here that are just pretty simple trigonometric uses on your calculator. But there are some problems here that we probably need to talk about. Maybe different than anything you've done before, but I think you're going to see this problem 39 not too bad at all. We're supposed to write a piecewise formula for the function, which means I want to write it in multiple parts. And I think it's pretty clear I want to talk about this portion, this line segment. I'm going to call it A for right now, and this segment B. And if I just want to talk about A, pretty clear what's going on here. A is a line with slope down 1 over 1 that passes through y-intercept 1. So A, if I was just writing A, could be y, or f of x, equals slope of -1 times x plus 1. And B, it's implied, I believe, this is the point 1, 1. So this is a portion of the line. It would have y-intercept of 2, but it also has slope -1. So that would be y equals slope -1 x, but y-intercept 2. But that's not piecewise function. That's the entire lines of the entirety of both of those lines. So piecewise function, I'm going to go f of x equals. Sometimes it looks like -x plus 1. Other times it looks like -x plus 2. But it only looks like -x plus 1 from here, while x is 0, and 0 is included, until 1, but not quite including 1. If you can see, that's an open circle. So 0, therefore, is less than or equal to x, which in turn is less than 1. And then the graph looks like -x plus 2, starting at 1, and that's a solid dot, and continuing until 2, and that's also a solid dot, and that's why it's less than or equal to. So a little bit different, not too bad. Okay, let's take a look at 41, and I've got a mistake here on 41. As you'll see, just repeated the same problem. So we're just going to do the top portion of that. Some people call this fog, -1, and I guess if you know what that means, that's great. I really prefer when I see this to read it as if it was this, f of g of -1. In fact, I really would almost rather look at it like this because it becomes so clear to me what to do. I'd start inside a parentheses, and I'm driving -1 into this factory right here. And g is a factory that takes things and puts them right there. So that would give me f of 1 on square root of -1 plus 2. So that is f of, that's -1 plus 2, 1, square root of 1, 1, 1 divided by 1, 1. So now all I have to do is drive 1 into f, and 1 into f. F is a factory that takes things and puts them right here. So that is 1 on 1, or just 1. Okay. Probably be a really good time to pause this and just go ahead and try g of f of 2. Okay. So g of f of 2 could be written as g of f of 2, and it becomes pretty clear what I do. There's going to be a little bit of cleaning up that has to be done on this problem in a little bit, but let's go ahead and start that process. Putting 2 into f is easy enough. I get g of 1/2. G of 1/2, g is a factory that takes things, puts them right here, adds 2, takes the square root, puts it underneath 1. So 1 over square root of 1/2 plus 2, or 1/2 plus 4/2, 5/2. Well, we might leave it in this at times. We might leave the answer like that, but I'm certain for AP test You'll not want your answer to be left with a radical in the denominator, so we're going to rationalize that. I'm going to multiply by root 5 halves over root 5 halves. And there's a couple ways you can go about doing this. That gives me square root of 5 halves over 5 halves. But dividing by 5 halves is the same as multiplying by 2/5. And now, since this is square root of 5 on square root of 2, I'm going to rationalize the numerator. Can I do that? Of course, I'm just multiplying by 1 here. So I get 2 times square root of 10 over square root of 2 times square root of 2, 2, all on 5. Well, that's nice. I end up with just plain old square root of 10 on 5. Okay. A little clumsy, but process not too bad. Okay, 43. So here, when it is just f of g, like back here we had find f of g of -1. That means I'm putting -1 in. When it just says f of g or g o f, then this really means I'm finding f of g of x. So similar for this would be g of f of x. So the first thing I want to find is f of square root of x plus 2. Well, f is a factory that puts things right here. So that becomes 2 minus square root of x plus 2, all of it squared. Or 2 minus, I'm subtracting everything. Well, we know that square root of x plus 2 squared is x plus 2. So I'm going to go all of x plus 2, and that gives me, distribute the negative, a negative x, 2 minus 2, just plain old negative x. We'll come back and talk about domain and range in just a moment. Let's go ahead and find g of f. So I want g of f is 2 minus x squared. And g is a factory that takes things, puts them right here. So I get square root of 2 minus x squared, but still plus 2, or square root of 4 minus x squared. Okay, so if we're going to go f of g of x, that means I need to start with values that I can put in for x, and that has to be able to go pass through g successfully. And if I look at this final answer and I don't pay attention to the process that went on, I would say, well, I can take any number I want and multiply it by -1. But let's look at the process. The process, first, I have to go through the g factory. Do we have any problems here? I can add 2 to any number I want. Can I take the square root of any number I want? No, it must be non-negative. Therefore, my domain, x plus 2, has to be greater than or equal to 0. So x has to be greater than or equal to -2. We'll come back and talk about the range on that. Let's go to domain here. The process of this is really g of f of x. If I looked at this, I'd say, hey, I've got some concerns here what x can ultimately be, because, yeah, I can square any number, but 4 minus x squared has to be greater than 0. Let's see the process. Put x into f. Can I square any number I want? Yes. Can I subtract any number I want from 2? Yes. So I have no problem until I get through into the g factory and I realize for my domain, 4 minus x squared has to be bigger than or equal to 0. So I'm going to treat this as an equality, and I'm just going to solve for x squared. 4 equals x squared. Therefore, x equals plus or minus 2. On a number line, I'm going to handle that right up here. That means that negative 2 and 2 are pretty interesting values for me. Since 2 makes this 0, I can touch 2. Negative 2 makes this equal to 0. I can touch this. Try a value between. If I put 0 in for x, 4 is bigger than 0, so this is my good zone. So my domain is negative 2, including negative 2, until I get to 2. Okay, range, always trickier. Range, I love my calculator for, but we're going to go ahead and do that without it. This function became negative x. I know what negative x looks like. Negative x looks like this. And we would say the range of this goes on forever. However, we are only allowed to consider the portion of this graph that's to the right of negative 2. And to the right of negative 2 would be right here. Therefore, my range, the highest it ever gets is 2. And it can go down to negative infinity. Of course, that's a terrible way to write this. It should be negative infinity up to 2, including. Okay. All right, let's take a look at the graph of this guy. Well, if I put in 2, I get 0. If I put in negative 2, I get 0. If I put in 0, I get 2. And if I put in 1, I get square root of 3. And if I put in negative 1, I still get square root of 3. I think we've got perhaps maybe half of a circle going on here, or part of a parabola, maybe more like. But I definitely have a shape that seems like it's going to fit in here. So, is it parabolic? Is it circular? Is it part of an ellipse? That's a study for another time. But let's take a look right here. I definitely know my range. My range, the highest I ever get is including 2, and the lowest it ever goes is just to 0. So our range is 0, including 0, up to 2, including 2. Again, great problems once you get this function to take a look at on calculator, but manageable. Okay, we spent a little bit of time last year talking about parametric equations. Now, if you took regular pre-calculus, you may correct me on that, but here's an example of parametric equations. Parametric equations, x is based on the value of t, and y is based on the value of t, and we don't really plot t. So I'm going to set this up as you're kind of familiar with, like the first kind of type of graphing you did when we were graphing any type of functions, probably graphing lines, is you created a t-chart. So I'm going to create a t-chart actually with t. I'm going to choose a value for t. I'm going to find out what x is. I'm going to find out what y is. And you can do this on your calculator and play along with these trig functions. The values of t I can use are 0 up to 2 pi. And I'm going to choose some strategic values here. I'm obviously going to choose 0. That's where I'm starting. And x, and so we would think of t as time. At time 0, x is 5 times cosine of t, of 0. All right, real quick refresher. Here's the graph of y equals cosine of x. It looks like this from 0 to 2 pi. So cosine of 0 is 1. Sine, similar, from 0 to 2 pi. Sine of 0 is 0. Oh, let me back up here. Cosine of 0 is 1, so that's 1 times 5. 5 here. Sine of 0 is 0. As we see, sine of 0 has no height. Times 2 is still 0. I'm going to jump right to 90 degrees or pi on 4. Pi on 2, thank you. To pi on 2. At pi on 2, cosine is 0. Times 5 is still 0. Sine is 1. Times 2 is 2. Let's jump to pi. Those are our nice defining values of our curves. Cosine of pi is down here at -1. -1 times 5, -5. Sine of pi is 0. 0 times 2, 0. Let's go to 3/2 pi. 3/2 pi. Cosine 1/2, 2/2, 3/2 is back to 0. 0 times 5, 0. Sine of 3/2 pi, 1/2, 2/2, 3/2 is down here at -1. -1 times 2, -2. And when I get to 2 pi, I'm back to the same values I had at 0. 5 and 0. So if I just graph those points, I've got a point at 5, 0. I've got a point at 0, 2. I've got a point at -5, 0. And I've got a point at 0, -2. And then I got another point back here. And we may need to fill in some gaps with some other angles to convince ourselves that this is an ellipse. I will leave that to you if you're curious to find some of those, or try graphing this on your calculator as a parametric. But this guy is an ellipse. It's a nice ellipse. It's centered at 0, 0. So next we are supposed to find a Cartesian equation of the, graph, identify the initial and terminal point. So this is t equals 0 right here. This is t equals 2 pi. That's where we're allowed to go through right here. And our direction of the curve as t increased went from this point to 0, 2. So our direction can be indicated that way. So that tells, we start here, we go around, we stay on the curve until we're back here. Okay, ellipse. Do we remember our equations of ellipse? Well, this is a pretty easy one. This is going to be x squared on plus y squared on equals 1. X squared on what? Well, from the center, our major vertex on the x-axis is 5. This is 25, 5 squared. Our b value to the minor vertex is up to 4. Okay. So a lot going on that problem. Hopefully quite a bit of it's on his review. Okay, so here's another problem like that. Let's give this guy a look. Straighten this paper out just a little bit. Okay, same exact thing. So I'm going to create my t-chart where t is going to give us values for x and values for y, and we're going to do those together kind of in our head. T is running from -2 to 4, so I think I'm going to choose values of -2, -1, 0, 1, 2, 3, 4. Maybe we don't need all those, but I don't think it's going to take too long. All right. I think I'm just going to do all of the x's first. When t is -2, that's 2 minus -2, 2 plus 2, 4. T is -1, 2 plus 1, 3. T is 0, 2. T is 1, 1, and we see what's going on here. T is 2, 0. T is 3, -1, and -2. For y values, when t is -2, we get 11 plus 4, 15. When t is -1, we get 11 plus 2, 13. When t is 0, we get 11 and 0, 11. I see what's going on here. 9, 7, 5, 3. Let's double check. When t is -2, I'm sorry, when t is 4 down here, I get 11 minus 8, 3. So I'm feeling pretty comfortable with that. So we're supposed to sketch that. I don't sketch t. I might refer to it a little bit later. I see my x values are mostly positive. My y values get big and positive. So I'm going to allow for that. X is running -2, -1, 1, 2, 3, 4. And y, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I've got a point at 415. That's not any old point. That's my point when t equals -2. That's my starting point. I've got a point at 313. I wonder if these are linear. I've got a point at 211. It sure looks like they're linear at that point, and I'm going to believe they are. And I've got a point at -2, 3. And if I was really good on this, I've got a point at 0, 7. They'd all look like they were in a straight line, but I didn't have the graph paper. But we look like this. Cheat a little bit here. So this is my initial point. It is going in this direction. You can put that arrow on there anywhere. Solid dots because we can be equal to at the beginning and the end. And this is my terminal point, t equals 4, right there. So it gives us some idea of time. From 2 days ago, we were here, and 4 days from now, we'll be here. Gives us direction, time. So what is this line? Well, this line we found has a y-intercept of 7. And by the time I'm over to 1, I'm up to 9. It's going up 2 over 1. So that is y equals up 2 over 1, slope of 2x, y-intercept 7. But is there something missing here? It's not that entire line, is it? What portion of that line are we dealing with? It certainly is not all of it. We're only dealing with x values from -2. Is that right? From -2 to 4. From -2 to 4. So it's -2 is less than or equal to x is less than or equal to 4. We don't want to claim that this is the entire line. Here's a word for you. Give the parametrization for the curve. A line segment. Parametrization. Well, that means they want us to write it in this form. Well, it's a line segment. It would be easy to write it in the other form. Well, let's take a look at it. -2, 5. I need to go to the left. I need to go to the right, but mostly up. All right. So let's just take a look at that guy for a second. -2, 5, 4, 3. They want this line segment right here. And those are our endpoints. Doesn't really say where we begin, but we'll say this is our beginning point right here. Okay, I can get from here to here by x and y. I can go over a little bit down, over a little bit down, over a little bit down. I can go in like 2 steps, over, down, over, down. I could go in 3 steps, over, down, over, down, over, down. I could go in 1 step, over, down. I'm going to treat this as though I'm going in 1 step. So how far over do I go? I go over 2 and 4. I go over 6, the difference from -2 to 4, or 4 minus -2. I go over 6. I go down from 5 to 3. So down 2. So I'm going to treat this as though I was going to do all of this in just in those 2 steps. Over 6, down 2. So every time I move now, I'm going to go over 6, down 2. From here, if I continued, I'd go over 6, down 2. So my x value, where did it start at? -2. What am I doing to it each step? Each time unit, we'll say. I'm moving 6. If I move 5 time units, I move 6 times 5, 30 to the right. If I move t time units, I move 6 times t. Does that make sense? Why? Every time unit, I'm moving down 2. If I move 10 time units, then I'd move down 10 times 2, or 20. 7 time units, I'd move down 2 times 7, 14. T time units, down 2 times t. So y, what did I start at? 5. Where am I? How far am I going down? Minus 2 every single time unit. And all that's left is, what are my values of t? Well, if I put in 0 for t, I'm at my starting point, negative 2, 5. So I'm going to say 0 is less than or equal to t. If I put in 1 time unit, look where I get. Put in 1 time unit for t, I get negative 2 plus 6. 1 time unit for t, I get 5 minus 2. So just to 1. Now, this part of the answer could vary. I could have done this, I could have split this into 6 steps if I wanted to. Over 6 down a third, over 1 down a third, over 1 down a third, over 1 down a third. I could have split it into 2 steps, any number of steps. I just chose to make it 1 step. I think you can see why I would do that. Okay, another good time for you to pause and try. You haven't probably done anything like this. Parametrization of this. I'm still going to go ahead and draw this, but you might want to pause and then come back and turn this back on play. Okay, we need a ray at 2, 5. Starts at 2, 5 and passes through negative 1, 0. So my ray looks like something like this. Don't bet on that necessarily being the y-intercept. This isn't to scale. So this is what my ray looks like. So, but what do? I could say I go over and down, 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 and get to here. Or I could just say I go over to the left and down. How far over to the left do I go if I went from 2 to negative 1? I'm moving 3 units, but that's to the left. I'm moving down from 5 to 0. That's represented with a negative 5. So x equals, where did we start x? At 2. What are we doing? Moving left. How far? 3. How often? Every time unit. Y equals, where did we start? 5. Where are we going? Down. How far down? 5. How often down? Every time unit. How about our values for t? When t equals 0, I've got 2, 5, and that's a good point. It's my starting point. So 0 is less than or equal to t. How far are we letting t go? Not just to here. Don't forget, that's a ray. We're letting t we're going to take more and more and more steps. So either 0 is less than or equal to t, or t is greater than or equal to 0. Okay, a little different. Hopefully you follow that. You might want to look at that again. All right, find f inverse. Show that f of f inverse is the same as f inverse of f, and they both equal x, because that's what inverse functions do. They turn things back to x. In other words, here I'm starting with x. I'm changing it. For those of you in honors pre-calculus last year, we're putting a star on that star-bellied Sneetch's, or we're putting a star on that Sneetch's belly, and we're turning it into that. And then I want to run this through a function and turn it back to here. On the most base level, sounds really simple. It's simple to memorize, sometimes tough to understand. All inverse functions do is they turn y's into x's. So since this is just a fancy name for y equals 2 minus 3x, to find f inverse, I'm going to turn y into x and x into y and solve that for y. Solving this for y, I'm going to add 3y to both sides. I'm going to subtract x both sides, leave this plus 2 over here, and y equals negative x plus 2 on 3, but that's really what f inverse of x is. And now we're just going to make sure that actually works by finding f of f inverse and f inverse of f, and make sure, are they really inverse functions with one another. So f of f inverse is f of negative x plus 2 on 3. Well, f is a factory that takes things and puts them right here. So this becomes 2 minus 3 times big mess negative x plus 2 on 3. That is f of f inverse. So this is 2 minus, the 3's cancel, negative x plus 2. And then 2 minus the 2 cancels negative, I just get x. So that's good. And now I'm going to just make sure it works the other way. F inverse of f. F is 2 minus 3x. So I need to put 2 minus 3x into this factory. That becomes the opposite of 2 minus 3x plus 2 on 3. Or negative 2 plus 2 cancel, negative cancels negative, 3x on 3, or x. And we got it. Okay, here's a problem. I would bet there's some temptation to like, oh man, I got to get my calculator for this one. And maybe your calculator can do this, but this isn't a calculator necessary problem. When we have variables in the exponent, logarithms are our friend. And since the base of this exponential is e, log base e is our friend, that is ln. We want to isolate the exponential. So in other words, if there was a 7 out in front of here, 7 times e, I'd want to divide 7 first. But since the exponential, the exponent and its base are all isolated, I'm ready to take my favorite logarithm for this problem, ln. ln e to the negative 0.2x equals ln 4. And we can do that because logarithms are 1 to 1. Okay, well, last year I taught people to read this, I'm going to put an e here as though it's the base. I taught people to read this as an exponent, or a logarithm is an exponent that turns its base into its argument. Base e, log 4. So this is the exponent that turns e into e to the negative 0.2x. This whole thing is the exponent that would turn e into e to the negative 0.2x. What could it be? Of course, this is negative 0.2x equals ln 4. Multiply, if I divide both sides by negative 2, that's the same as negative 0.2. That's the same as multiplying both sides by negative 5. Notice if I multiply the left by negative 5, I get positive 1x. So I get x equals negative 5 ln 4. Okay, so that's an exact answer. It's all going to depend on how the question's asked, whether it asks for round to 3 decimals. If it asks to round to 3 decimals, I just might take this and graph this and graph 4 and see where the two intersect. But if you're asked for exact answers, your calculator's not going to give you this. Okay, and 61. Kind of a fun one. A portion of a function is defined on negative 3 to 3. Well, I look at this function down here, and these are the same, obviously. We got two parts to this. It only shows the graph from 0 to 3. So it goes to the end, but it's missing negative 3. It's missing this part to the left. What happens over here? It says complete the function if it is even or odd. So I'm going to treat this one as my even. Even functions like, for instance, y equals x squared. A function is even if the height to the right is the same as the height to the left. So this function to the right is up 3. To the left, it better be, you got room for that? It better be down 3. This function to the right is down 1. To the left, it better be up 1. And those are connected. This function to the right 0 is 0, so to the left 0 should be 0. Oh, you know what I just did? I just did the odd function. That was terrible. but I'm not going to redo it. So that's our odd function. Backtrack here. An odd function like y equals x cubed the height to the right is the opposite of the height to the left. So let me backtrack on this. I apologize. If my height to the right is up 3, my height to the left should be down 3. So there's the odd function. Even. The height in both directions is the same. So if my height to the right is up 3, my height to the left is up 2, my height to the left 3 should be up 2. If my height to the right 1 is down 1, my height to the left 1 should be down 1. And if my height to the right is up 0, my height to the left should be up 0 as well. And you see the symmetries we get. Even function, symmetric across the y-axis. Odd function, symmetric 180-degree rotation about the origin. Okay, there's a couple more problems in that review set. We can take a look at those, but this would be a really good representation, as well as the handout you received in this class on day 1. This would be a really good representation of what our chapter test for 1 is going to be, and that's going to be coming up very soon. Thanks for tuning in.